Okay, now let's talk about those spanning trees. I mean, first of all, I just would like maybe to check some kind of an empty. Can I have here have some kind of an empty slide? No. We stopped this before. Add new slide. Yeah. Why? Because I would like to just show you something. Now imagine that we have some kind of graph, and I just would like to mention why do we need those spanning trees, for example. And the example that I found just some kind of interesting example on the web, and I would like to share that with you. Now to explain the benefits of CDE. Let's say we have some kind of graph here that shows. Anyways, I'm just trying to show different type of connections between different vertices. But let's say that these are some kind of offices of a company, and this company has like these how many offices? 1, 2, 3, 4, 5 offices, and these offices need to be linked in some kind of a network. So in order to link them, well, there's a cost between linking each one of these. Let's say if they just talk to the company that, like the telecommunication company that they can lease the lines from, it gives them some kind of costs. To link between A and B, it costs 7,000 reals, for example. Between A and E, that's 10,000 reals. Between A and C, that's 8. Whatever, I just put some kind of numbers. But that means that this is how much it costs to link between each one of those two vertices in the network. So these are different offices, and these are the lines that can be used to connect these offices. Now what we'd like to do is, because we are working for a network, we would like to have some kind of a network connection, so we don't need them to have like a redundancy in terms of like two ways to go from one to the other. I can just, for example, go from A to B, and then from A to B, A to E, and then A to C, and then A to, oh, there's no A to D, I forgot to draw that. And yeah, this is 2.
E to B.
And there's one missing? Yeah, okay. Thank you. So I don't have to.
And you forgot also the cost of E to C.
E to C, there's no cost?
Yeah.
This is the 8. E to C. Oh yeah, there's no cost. Let's put 7, 30. Okay, that gives you 13. Here. So let's say that these are the costs. Now if I'd like to connect these, I can just do something like this, for example. So, which means if I'd like to call D, would like to call C, it has to go through A. But that's fine, there's a connection, there's a way how to reach any vertex. Now the cost of this is, I need just to sum up all the costs that I have. For example, from A to B, that's 7, and then from A to E, that's 8, and then that's, I don't know, 2, I guess,
2, yeah. And 10.
and then 10, which means the cost is 12, or maybe 10, 20, 27. But if I do another option, now what if, for example, I just do something like this, from A to E, and then from E to D, from D to C, and from, let's go from, because this is the cost is less, from A to B. So I have something like some kind of a C-shaped network. Now what is the cost of this? Is 7 plus 10 plus 11 plus 15, which is obviously 36 plus 7, 42. So these are different possibilities, and hence each one of them is a spanning tree. That's the spanning tree. So we can have a lot of different kind of spanning trees. Is that when you do this kind of traversal of a graph, the resulting of the traversal is a spanning tree, which obviously does not have any cycles in them in it. It just you can go from one vertex to any other one in a undirected graph. Of course, we're not talking about directions here. Just an undirected graph. You just go from one vertex to any other ones. And now the usefulness of this spanning tree is just we like to find the minimum spanning tree, because we don't want to pay a lot of money to link between our 5 offices. So we'd like to, based on these different possibilities, which one is going to be the minimum. And that's the talk about we're going to be talking, inshallah. And there are two kind of algorithms that are used. One that is like Dijkstra's algorithm is called Prim's algorithm, and there's another one which is more efficient that we're going to be talking about. Sorry? No, I just forgot the name, but it's let me just find it. So Prim's algorithm is this one, like the Dijkstra's algorithm, but there's the other one is Kruskal's algorithm, which is much, I mean, first of all, much simpler and also more efficient. So that's the idea behind those spanning trees. So it's some kind of a type of optimization problem. Now let me just move on and keep going. So the spanning tree is a simple connected undirected graph, and in which it's a free tree. That means there's no kind of root. It's not like a tree that has some kind of root, but it's a tree that means there's like no redundancy of the connections between two vertices. So we don't have like two different paths to go from the same two vertices. I mean, sorry, two edges between the same vertices. And then this is the with the number of vertices minus 1 edges that connects all the vertices to the graph. So basically, if we have 5, like in the example that we had, like hold on, let me just find it down there. Where was it? I just erased it. Okay, I just erased it. So when we had 5 different offices that we had, A, B, C, D, A, B, that's kind of scary, and E. Now one of the things that we added up is to have, like we said, this kind of an example of a spanning tree that connects them all. That means it have 5 minus 1 edges. That's how a spanning tree is going to be. If you look at another configuration or another answer, if I do something like this, and then this, this, and this, it's going to be 1, 2, 3, 4 again. So it's the number of vertices minus 1 is going to be the number of edges. So the spanning tree is a tree that is connected, not directed, undirected, and where this number of edges is the number of vertices minus 1. And then it is connected and acyclic. Acyclic means without cycle. Acyclic, no cycle. This is what it means. So these are spanning trees. Now, if you have some kind of a tree and then you do some kind of a traversal, depth first, breadth first, you're going to end up in a spanning tree. That's the kind of traversal that gives you a spanning tree. That's what I was trying to explain. At the end, if you have 1, 2, 3, 4, 5, 6, that means I have 6 vertices, means 5 edges. 1, 2, 3, 4, 5. Just enough to connect each one of the vertices. That's it. So now, when we would like to be interested in, we're interested in finding the minimum spanning tree. If we have something like this, then there are different type of trees that can possible with this. Within 4, we have 16 possible spanning trees, which basically all the possibilities of linking 4 things together. And each one will be the cost, and we're interested in having the cost. And sometimes you have more than one answer that is going to be having the minimum cost. Like for example here, if I'm connecting these, I have a total cost of 6, but if I'm connecting, let me change the color, this, a cost of 6 as well. I hid the one that was here, but you got the point. We might have more than one minimum, but the idea is we would like to find the minimum. Now, how can we find a minimum in a spanning tree? I will start with the easiest one, the Kruskal's algorithm. First of all, because it's easy to follow up and it's kind of optimized. It doesn't waste a lot of time as compared to this Prim's algorithm, which is close to, it's like Dijkstra's algorithm but applied to the spanning trees. Now, how can we find that? Now, this is the some kind of a summary. So what we do, I mean, it looks here a bit kind of not as simple, but let's have a look. Now, if this is the tree that we have, how to build this spanning tree is going to be doing just one very simple thing. Always, you just look at the smallest cost of all these here. Which one is the smallest cost?
5.
No,
3.
3 is the smallest cost. So we just draw the tree. The tree. We just put those that are going to be just the smallest cost, without, of course, including the same edges. I mean, the same edge again. So now what we have, 3. This is what we built. This is what we have. The only thing that we have is the one that costs 3, and then it's done. Of course, we should not, when we do that, we don't want to have any cycles. I would like to be able to traverse all the vertices. So when we're going to be checking now who's next, it's 5. So we're going to be adding 5 to the tree. So in our spanning tree, at this point, after adding the next one, we have these 3. They're not connected, but we're not there yet. We're just building the answer. Then we keep going. So we removed 5 after removing the 3. What's the next step?
6.
The next smallest is 6. So that's why we're going to be adding it without a problem. It doesn't create a cycle, so we add it. And then what's the next one? 7. And there's no cycles if I add the 7, so that's why I'm going to add the 7, and there's no cycles. I'm just going to show what we're at. So the 7 is going to be removed. Now, which one is the smallest? 8. 8. If I add the E, does it add any cycle? No. So I'm going to add the E. Now, which one is the smallest again? 9. But 9 will create a cycle, not going to be an option. 10, 11, 12. 12 is from F to C. So it's going to not create any cycle. We're going to add it. And this is the 12 that we just added. Okay. And then what next? We just keep checking. 13. Can I add 13? From E to, if I put this 13, I'm going to link this with B, which will give me a cycle. What cycle? Because if I put E to B, so that's what I'm going to be having. It becomes a cycle. A, B, E, G, F, C, A, B. So this is a cycle. So I don't want to have that, so I'm not going to add that one. So as long as you don't have any cycles, you just keep adding all the vertices, so all the edges.
Now, any additions will be cycles. So what we do?
We just stop. I mean, basically, when we have all the vertices, we just stop. We don't need to check, but I just wanted you to see why we're not going to be adding the others. But as long as we're connecting all the vertices, that's fine. I mean, we know exactly how many edges we need. When we have this graph, counting how many vertices gives us how many edges we need to find in our spanning tree. Now, if we have how many? 1, 2, 3, 4, 5, 6, 7. That means I have 6 edges. And once I have those 6 edges, I just stop. So that's how we build the spanning tree in using this Kruskal algorithm. Now the fun part is Prim's algorithm, which involves the same idea that we were doing, but this time it's going to be similar to, we need to start from somewhere. So that's the difference between the Prim's algorithm and Kruskal's algorithm, is that in Kruskal we did not need to fix a starting point, while in the Prim we have to, because it's based on Dijkstra's algorithm, and the Dijkstra's algorithm is needing to know from where we start. Now let's say you would like to apply this to here. We start by initially putting the 0 to the starting point and infinity to the rest. Now from that we just look at, from this one, which one costs less? Is obviously the D. So that's why from the A I can go from A to D, which is the one that costs less, but I also need to put, because all of them, the initial cost is infinity. From A, if I go to D, it will cost me 1, but from A, if I go to C, previously it was costing infinity, now it's going to cost 8. And from A to B, it's going to cost 13, so less than infinity, so I'm going to do this. And the rest are going to stay the same. But I need to remember what was the precedence, the predecessor of that took me from here. When I did this, no, this is the last thing, this is the last result. But what I initially, from A, I want the B, the predecessor was A, the C, the predecessor was A, and then the D, the predecessor was A. And then A is done. So I finished with A. Now, from where I start, so just look at the minimum, that's the D. Okay, so starting from the D, I need to see all where I can go from. From D to A, basically A is done, so I'm not going to go to A. So from D to C, it was infinity, so I'm not going to, I'm now find a smaller one, that's 5. From D to E, it was infinity, now it's 4. From D to F, it was infinity, now it's 5. So that's why when I put this, that means the C, before it was 8, I found a shorter path to go to C, which costs 5. So that means now the predecessor from C is not A, but it's D. And the predecessor from E is D. And from F is D. And then I'm done with D. What is next? Just look at the smallest cost that we have. And then we have 4. Now this 4 is the E. Okay, from the E where I can go. Now I selected the E. From E I can go to D, but D is done. E I can go to C with the cost of 3. From E I can go to C with the cost of 3, which is smaller than 5 that I had before, which means this is going to be the 3. So instead of, remember it comes from a shortest cost from D, now it's going to be from E, but I put 3 here. And then from E to F, it was costing, now to go to F it was costing 5 when it goes through D, but now if you go through E it will cost 2, and then, which means now I'm going to remove the D to be the predecessor and make it E, and the cost is going to be updated as well. And then I'm done with the E. E is done. And then I look what's the minimum that is remaining, that are not visited. We have B and C. C with 3, so I'm going to check with C. Now from C, where I can go to A is done, D done, E done, B is what's remaining. So from B it will cost me 15. So it's more than the 13, so I'm not going to do anything. And there's nothing else to do. I'm done. And then from B, nowhere else to go, because it's all done. F, done. And now I have this list of trees with some kind of predecessor. So that's why you see the predecessor is A, here E, this is why the result is E, why it's A, why it's D, and why it's E. So it was D before and then it came to E. And that's how we build it using this Prim's algorithm. So how do we know now? We have, if we'd like to find the predecessor from each one of them, so how to build the tree and to basically to find the cost. From each node you just look at the predecessor. So F, the predecessor of F is E. So we have this one, and then from E the predecessor is D. From D the predecessor is A. And then from C the predecessor is E. And BA, and that's it. And that gives us this spanning tree with the cost of 23, and that's the minimum cost. That's Prim's algorithm. So the difference between the two is that this one does not need a starting point, it just looks for the minimum cost and just start building just the spanning tree just with edges. As long as we don't have cycles, we keep adding from the minimum and keep going. While this one, the Prim's algorithm, which is based on Dijkstra's algorithm, is just going to do the same thing, but the difference between Prim's and Dijkstra's algorithms is that in the Prim we just have a total cost. We just keep accumulating the cost. We have, for example, if we go from A to D, we just have 1, A to C 1, 8, etc. But from D, let's say, to F, we don't put 5. We just put 5 plus 1 that we had, which make it 6. So we just have some kind of total cost of the path, but we're not looking for some kind of a path in the Dijkstra's algorithm. Now in Prim's algorithm, we just put the values themselves without accumulating the sum of that. Yes, you had a question.
Is the both algorithm will give the same answer?
Not really. No, it doesn't have to be always the same answer, but they always find the minimum. Remember, because sometimes you might have 2 minimums or 3 or different possibilities that are going to be the minimum, having the minimum cost. So they might not lead to the same graph, but they will always find the minimum. You get my point?
So the minimum will be the same, but the graph will be different?
No. But the value of the minimum will be the same, yes. But the graph, the tree will be different. Like for example here, what's the total cost? The minimum cost is 6. But the graph, the tree is different. So it might be the same, but it's not guaranteed. For example, if we'd like to build this using this Kruskal algorithm. Now what is the thing that we're going to do? How are we going to build it? The first thing is we look at the smallest one, which is AD, sorry. And then we look at the 2, so it's going to be EF, and then C, we add it, no problems.
D, D,
E, D, we build it, okay. And then
CD.
CD, but we can't.
Makes
There's a cycle,
E.
so we're not going to be adding the 5. And then what's next? 8. It will make a cycle again, so we cannot add it.
There's only 13, which is A, B.
And then 13. And now we have connected everything. In this case, it's the same tree. I'm sorry?
Why not FD?
Why not?
FD.
FD?
A cycle.
FD? Because it's a cycle. Yes, I forgot to pay attention to it. But if I add it, yeah, let me just roll back. We added this one first, then this one, and there's no problem.
Then 3.
Then, okay, hold on. Why did we start with CD and not DF? Well, there are different ways. You can choose one of them. Now, but which one we're going to choose? Let's say we
Start with the 3,
with
4.
with alphabet. Oh, sorry, you forgot about the 4. Yeah, and the 3, and the 3 4 before, and then the 4. Now, which one I'm going to check? This one or this one?
C.
We should check.
So we have CD and DF.
Yeah, but C, at least.
EBC.
I'm going to start with CD first. It's not going to work out. I need to check with DF. Not to work out because there's a cycle. That's the problem. And then the next one is going to be 8, which is cycle again. I cannot do that. And then what is remaining, 13 and 15, only one of them. 13 is the smallest, and that's how I get the same result actually. So in this case, the two methods will give us the same result. But in some cases, especially if there are more than one way to find the minimum, then we might have different results. Yes?
What if E to C equal 10? Let's see.
What if E to C, this one, equals 10? Okay. So, how to build the tree? Same idea, we start here. This is the 1, and then the 2, and then there's no 3, so we have now 4, and then 5 is going to create,
Cycle.
now 5 this one, there's no cycle,
No cycle, so we add it.
and then
The 13.
8 first is a cycle,
Cycle, so we add it.
so 10
Cycle.
cycle, so we're going to use it, and then 13 is going to be used, and then 15 we don't need to. So it's going to be this type of result, which is different from here, but that we don't have this one, but we have this one, how we connect to the C.
Because you will check the 3, you will make it 10 in the schedule, and he will take the 5 because 5 listed. That's something.
Yes,
Taking something back into the
so it will always try to find the minimum spanning tree this way. It will always be connected. A spanning tree is always connected. One of the conditions, it's always connected. It has all the vertices from the original tree, and it doesn't have a cycle. If it's not connected, it's not a spanning tree. Is that okay? Yes. Which one?
the 3.
The 3? Well, you have that on. So connected means there's an edge between every vertex. And what does this mean though? Because this is just a representation that says this is the original graph, this is the spanning tree. The original graph has a number of vertices, number of edges. This is the base, the derived, or the spanning tree derived from this one. That's going to be having this kind of number of vertices, number of edges. Now the vertices are the same because we don't leave out any vertex. and the edges are going to be another set different from this one. And here this I don't know how you call this, E prime, or I don't know how to call that, is going to be equal to
E.
this represents what?
Edge. All the vertex.
No,
of vertex.
the number of vertices. This is called the number of vertices minus 1. So the number of edges, actually I should have done this. The number of edges in this spanning tree is going to be the number of vertices. If I use this one or that one, is the same, because we said that they are equal. But I prefer not to, so you can just to refer to it, so you can see it. It's connected to that original one, and it's the minus 1. These are the number of edges. All right. This is another example. If we'd like to apply this Prim's algorithm to this one, before that, let me just show you, for example, what this table means. This is this Kruskal algorithm, which is going to check the minimum all the time, right? So what we do here, we just sort these based on the minimum. If we have like these edges, we just represent them from the smallest one based on their weight until the biggest one. And if we have now this edge, instead of calling it FC, we just start with the alphabetical order, so we call it CF and things like that. So that's if we have some of them that are on the same edge, the same weight, then instead of calling it DA, we call it AD. We start with the smallest one first, then the next one. So now basically what we do is that we have 2 and 2. Which one we start with?
A.
With the A. And then EG. And that means when we sort them all the edges, and then we just check the ones that we're going to be using. We're going to be using these ones, so we use them. Then what's the next is the 3. We have 2 of them, AB and FG. So we start with AB, and we have this FG that we use as well. And then we have number 4, which is AE and DF. We start with AE, it doesn't create a cycle, so I'm going to add it and check it. Now there's this DF, it's going to create a cycle, so I'm not going to include it. So that's why we have this here. So the DF is not going to be included. Now after 4, it's 5. It's EF. EF is going to create a cycle. I'm not going to add it. And then after the 5, there's the 6, which is the DE, not going to be added because it creates a cycle. And then what is remaining? 7, BE, which is same thing. So DE no, BE no. And then we have the 10. I'm sorry? BC? AC, not BC. AC. So it's not going to create a cycle. I'm going to include it. And then, so this means this is included. The remaining, no, cycle. This also cycle. So I'm not going to include them. And that's how you just get to this result. Now what if we applied Prim's algorithm based on the Dice-Kras algorithm? If we'd like to apply that, we need to start somewhere, because if you don't know where to start from, you're not going to be able to build it. But because the Prim's algorithm is always needs a starting point. So if we start from here, for example, so how do we represent that? Now if we need to have this kind of all the edge vertices, yeah, I'm going to present it this way, and then this is the weight and the predecessor. So we have A, B, C, C, D, E, F, and G. Now we start somewhere. To try to have something similar, let's start from A. So which means we start with the weight of 0, infinity, anywhere. Yeah, I just want to show the steps. Now the next thing is from A, I just need to find where I can go. From A I can go to B with 3. So I'm going to put this B3. And I remember that it's coming from A. And then from A I can go to E with 4. So this is going to be 4 from A. And then from A I can go to D with 2. And I remember it's A, the predecessor. And then from A I'm going to go to C with 10. And I remember that I'm coming from A. Next step, I finish with A. That means A is done. Just would like to change the color. Then, next step, I'm just going to take the list. So I'm going to start from D now. Okay, so first of all, I started from A, and then I checked it. Now I'm going to start from D, and I'd like to check it. From D, where I can go? D to A, done. I'm not going to go back to A because A is done. D to C, that's 12. But it's more than what I have, so I'm not going to change it. D to E is 6, more than what I have, so I'm not going to change it. D to F, 4. It was infinity, so now it will be 4, and I remember that I'm coming from D. Then D is done. Now the next step, let me change the color, just for fun. I'm going to find which one is the minimum. So D is done now. I'm not going to check for D. Let me just represent done by doing something like this. Okay, so it will be easy for me to find that it's done. Now, what is remaining? We have 3, 10, 4. So we start from B. So we select B. And then from B, where can we go? To A is done.
7.
To E is 7, which is more than this. So nothing is going to be changed. I'm done with B. Okay. What is remaining? Another color. We have E and F. Which one we choose? Well, let's start with E because in the alphabetical order. Now from E, I'm not going to A, B, or D because they're all done. I have F with 5. More than what I have already, so no. And then G with 2, which means it was infinity, now it's 2. And I remember I'm coming from E. Now E is done. I'm just remembering that E is done. Now we have 2 because it's smaller now, the minimum. Now from G, this is what I'm selecting. Let me just choose another color. Yeah. I hope it's not too bright. Okay. Now, from G where I can go, E is done already. I have only F with 3. Oh, I found smaller than 4. So, I'm just going to change this. It will be 3. And change is coming not from D this time, but from G. And I'm done with the G. And then what is remaining? From the 10 or 3, that's the 3, which is the F. Change the color. I don't know, this one. And then so now I'm in the F, and from the F there's nowhere else to go besides C with 15, but I have only 10, so I'm not going to do anything. So I'm done with F. F is done, and what's remaining is C. So that's it. I found this. So now with this result, what is going to be the tree? Let me just try to highlight in a different color again. Where's the color? So A, I start from A, but from A I can go to B and C and D. So A to B, sorry, this one, But let me erase something because it's kind of. Can I? Yeah. Let me erase all this so I can have a cleaner graph too. So I have from A to B, because from A I can go A is the predecessor of B, of C, of D, and E. And then now J is the predecessor of F. That means I have something like this. And then E is the predecessor of G, which is giving me this, which results in the same idea. But did you notice how much steps I need to do as compared to the Kruskal algorithm? The Kruskal algorithm is kind of straightforward because it just look for the minimum, check it, I'm going to edit or not. So it's more efficient, it takes less time as compared to this Prem's algorithm. Is that okay? So it's all about those spanning trees, and yes, we still have some time.